Okay, so we're going to talk about string matching automaton algorithm for string matching for finding all matches of a given pattern in a given string. So then the idea is to construct a DFA, deterministic finite automaton, to recognize the pattern P, the given pattern P. Not only that, we want to find out all appearances of P in a given string. Okay, so now let me open up a whiteboard. So that I can explain the idea. So for instance, we are given a pattern P, which has M symbols. So we call them P1, P2, PM, and each of these PI is a symbol in an alphabet. So we want to construct a DFA to recognize this pattern. So in particular, we let I denote a state. That means that I have seen to mean that I have seen the pattern or the prefix P of from 1 to I so far. Okay, so, and also when I is equal to 0, it is an empty string where I from 0 to 1, 2, up to M. So then this DFA will look like this. Okay, so we have 0, that's the start state, P1. So at 1, I have seen P1. On 2, I have seen P1, P2 because it's from the start state. So this is P3. And the last one is PM. Then I have seen the entire pattern. So this is M. All right. So this is the basic ones. But then we have to look at each of these states because they could take other symbols. For instance, let's say a certain state, let's say 2, right? So let's say I have a symbol A, and A is not equal to P3. So where this A should be pointed to. Okay, so of course, what we want to point it to is that you don't want to go to the zero. You don't want to go to 0 right away to start over again because this P2, for instance, P2 or P1, P2, because now this is what we have read, right? So if this is A, so this is what we read. If A is equal to P1, say A is not equal to P3, but A could be equal to P1, then this A, then this should just go to here because that's P1. So then we have this P1, then P2, P3, okay, instead of going to 0. So what that means is that, so this is the prefix. So this is P1 is equal to A, that means P1 is also a suffix of this string, right? So this is, so this string is P1 to A. And for instance, if P1, P2 is also a suffix of P2A, so that means if P1, P2A, if P1, P2 is equal to P2A, okay, then this A, that is, so that means we can just, so this P2A is equal to P1, P2. So that means when we just need a loop here. So that, let me erase this part. Now, if that is the case, okay, so maybe I will draw it here. 1, P2, P1. Okay, so A is not equal to P3, but P2A is P1, P2. So that means that since I have read P2A, so this is really just P1 and it's just P2. So so that means that I could then just look at the other one. So this will be P3. So this means, so now we generalize and change this 2 to any I. So that means that if I have, so this is, if on state I, so that means I have read this. The next symbol is A. So let's say the next symbol is A. So then where this string going to? So this, if A is equal to Pi plus 1, then of course we know it's going to go to A, going to I plus 1. Otherwise, we are going to, if A is not equal to Pi plus 1, so this should go to the largest. Let's call this state Q. Which is the largest. So this is largest value K such that P such that P one. So hold on. So let me draw a picture. So we are here. So this is my pattern. Okay, so where should I end up to? Should just be, so this entire, so this is a, this portion is underlined. So what we are trying to look for here is that I want to say that this part, because this A is also I read, so let's call this, okay. So this part is actually appears here. Okay, so this part appears here, and this case would be the maximum one. So that means so this, so if we let sigma of a string x denote the maximum value of k such that p 1 to k. Now this is a prefix of the pattern, is a suffix of the string x. Then what we want to have for the transition on state I, right? So the transition on, because I'm currently on state I, and I read A, then it should go to sigma. So the state is determined by sigma P11I A. Okay, so then this way we hope that it will recognize all appearances of the pattern P. So we're going to prove this fact in a moment. So right now, let's go to see our slides. Okay, so that's what I just defined. So that's sigma x equals the maximum value of k such that, so P1k, so P1k is a prefix of P, the pattern. That appears as a suffix of x, so that when you are on state, so x here you think of as an input, right? So when you, so at this time, then what you're going back should go to k. Okay, so so this is what the sigma x is, and if x is a suffix of y, then sigma x is less than or equal to sigma y. So this is clear because this just means that if this is y and x, so this portion is x, and then the sigma x, okay, sigma x is, so then let's say sigma x would be something P11k, which appears here. So obviously P1k, P1.k appears here, also would appear here. But then P1K is a prefix, so sigma y will also be the P1K appears here, right? So that means that this K so sigma y is at least greater than or equal to K. Okay, so this K is sigma x. So that's, remember this P1K is also, it's a fixed part, okay? Which may not be the prefix of y, but it is a prefix of the pattern. And so let me draw this again. Okay, so this is too small. Let me put it here. So let's say this is y. Let's say this is another string x. X is a suffix. And sigma x, let's say is equal to k. Then that just means that P1K is a suffix here. So let's say this is P1K. Then of course, because x is a suffix of y, so this P1K is also here. Okay, but it's possible. So that means a sigma y is at least k, right? It could be bigger. So in other words, maybe one pk plus 1 is also a suffix. Okay, so that means that sigma y is at least k. So this is straightforward. So now, as we said, that the finite automaton, the DFA we constructed, will use this sigma function. Okay, so now let me say that again. So on state Q, what I have seen the pattern so far is 1, 2, Q. So then on the string A, if A is PQ plus 1, then you go to Q plus 1. Otherwise, you would go to K. Okay, you will go to K. Of course, there's something here. So where the K is just equal to sigma, so this string A. So that's what this means. And then we're going to show that in doing this DFA, we can recognize all appearances of pattern P in a given string T. Okay, so what we're going to do is define a state function phi. So phi on epsilon is Q0. And phi WA is equal to delta. Now this is a state on phi W and then on A. Okay, so what we are going to show that for any, so T here is a given string. So for any prefix, this phi gives what we want. So that's equal to sigma T. So remember, sigma T is the, so this is equal to a state K. when k and when p1k is a suffix of t1I, and then from 1 to k plus 1, it is no longer a suffix. Okay, so p1k is not, so that means k is the largest. So we're going to show this fact. So that is a DFA we have, and once we have this, then you know that for t, we just keep reading, keep going through the DFA, and then count how many times the accept state is reached. Okay, and then we move backward by m links. Okay, that is the shift position. Okay, so each time I reach a accept state, then I will just go backward for m places. Then we get a shift position. Okay, so that's what we're going to prove. So in order to prove this, so let's first look at a simple lemma that for any string x and character a, or alphabet symbol a, we have sigma xa less than or equal to sigma x plus 1. Okay, so this is actually, if you draw say this is x, and this is a. So you want P1K as, so this is say as a suffix, P1K. Then of course, P1K minus 1 is a suffix of x. Then just plus 1. Then will be this one k. So that means that of course for sigma x itself without a, so maybe this is even p1 k plus 1 could also be a suffix, but with an a, then this is no longer true. So that means that this is true. Okay, so sigma xa is bounded above by sigma x. So this part is sigma x plus 1. Okay, plus 1. So it could be just this. This we know is absolutely true, but it could be longer, right? So this then is true. So looking at a picture is always easier to find out why it is true. All right, so now this is what we're going to show. So if Q, so if a sigma T I 1 to I is equal to Q, then sigma, so you get an A here, so this will just be equal to P1QA. So now remember, this thing just means that if you look at T, so this is from 1 to I. So this is T from 1 to I is equal to Q, means that 1, so this is 1 to Q is a suffix of T of from 1 to I. And then you add A. So this is P. So you add A here. And of course, this is going to be equal, right? So this A here, this is A here. So it's not going to be, so this is the largest Q such that this is suffix of I. So this is obviously true. So this is easy to see. And so you can look at this right up here. But if you just look at the picture, you immediately know this is the case. So let's just go over this bullets here. And so from Lemma 32.2, we get sigma T1IA less than or equal to sigma T1I plus 1, and this is equal to Q plus 1. And we know that P1Q is a suffix of T1I, so that's what we know. So then, of course, this whole thing with the A is a suffix of T1IA, hence, because it's a suffix, we previously showed that we have this sigma, because this is a prefix, so sigma P1QA is less than or equal to sigma T1IA. So now we just let R be sigma T1IA. Then we know that this is going to be less than or equal to sigma T1I plus 1. That's equal to Q plus 1. And then this is the length of the pattern P1Q followed by A. Now this is the length. Okay. So because both P1Q and P1R are suffixes of T1IA. Okay. Yeah, so R here just means that 1R is a suffix of that. And the length of P1R is less than or equal to P1QA. Because of that, right? So that means we know that P1R is a suffix of P1QA, hence this R is less than or equal to sigma P1QA, and hence sigma T1IA, which is less than or equal to P1QA. Because that's R is equal to this. Okay. So then combining these less than or equal to so this is sigma. Right, compare this, combine this, and this, they will have to be equal. So as you can see, all of this writing is just this picture. Okay, all this writing is just this picture. So if you see this picture, you immediately know that this is true, and then you just use words to represent, to describe that picture. Okay. So finally, we are going to prove this is true. Okay, so we do this by induction. So on I, so when I is 0, T10 is an empty set, and we know that the phi of T empty set is equal to 0. And this is just a sigma T1I, so this is at the very beginning. We haven't seen any pattern yet. We haven't seen any prefix of a pattern yet. So induction hypothesis is that we assume phi T1I is true, then we're going to show, so phi T1I is equal to sigma T1I, then we're going to show when I becomes +1, I +1, this is also true. So, so this is what we have. So we're going to prove this. So we let A be Ti +1. So that's what we get this. And by definition, this is equal to this. And then phi of this, by definition, is equal to Q. So phi, so this is a hypothesis, and then we assume this is Q. So that's where this Q is. And Q we know is just P1. So this, by definition of transition, is equal to delta P1QA. And P1Q, sigma P1QA is equal to sigma T1IA. Right, so, and that is T1I +1. So this is actually straightforward once we figure out this. Okay. So that means now on my DFA, I can so say this is my DFA. So P1, P2, up to M. And T here, we just match now because there are lots of other symbols here, right? So, so then so there are also other symbols. So when T comes in, we just read one at a time and do this matching and follow all of these edges, right? To look at, say, T1 here. If T1 is P1, then it's match here. Otherwise, we match the other edges. So you just keep on going, and then every time it reaches an accept state or a final state, then we just go backward by M links, then we know where that shift's place is. Okay, so that is the automaton approach. All right, so now let's look at an example, but before we do that, let's look at the pseudocode. So we construct a DFA, and then, so that DFA is just this transition function. Okay, so Q on TI, we go to Q. So, I'm sorry, we construct a transition function that's a pre-processing, and then now given the input T and the transition function, we just go through T by doing a matching of the label, of the link label of the DFA. Okay, so every time I reach the final state or the accept state, I'm going to print the shift station by moving backward M links. So that's I minus M. So that is my shift position. Okay, so now let's move back. Look at this example. So the pattern is AB, ACA. So maybe I will draw separately here so you can see the process better. So we got 0, A, B. Let me just finish the pattern. A, B, A, B, B, A, B, A, C, A. So 1, 2, 3, 4, 5, 6, 7. So that's 5. And 7 is the final state or the accept state. Okay, so now remember each of these, remember well here, then I have seen P1, 2. That's AB, right? Here I have seen ABA. So then for this, if now we have the alphabet is A, B, C. So this means that at state 0, I haven't seen any pattern. So that means if you have B, it's just still there. You have C, still loop there. And then if I seen A, so I'm going to move to this state 1. Okay, and then here I could have A and I could have C, right? So if I have A, that means I also have seen A, so that I will just remain. If I see C, that means I have to start from the beginning. So that's okay, if I go, so that's what it is, right? So let me erase this one. Okay, because I need this space, so let me just move this somewhere else. I need this space. Okay, so then from 2 here, so we got, if A go to 3, if I B, so where should I go to? So remember, so once I'm here, that means I have read A, B. Now if I have a B here, that means I'm looking at A, B, B. And none of these prefix is a suffix there. So that means I have to go to the beginning. I haven't seen any pattern yet. So that means I'm gonna change the C here. Then this B. Okay. And if a C, I also go there. Okay. Here on 3, if I read B, I go to 4. If I on A, let's see where we want to go to. So this just means I have read now A, B, A, A. So that means I can go to 1 because I have seen this A, right? A, B, A. So this is the longest prefix. That's also a suffix. Now remember, this A is the prefix of the pattern. So you just look at this. There's always the prefix of there's always the prefix of the pattern on this direction. So that means from 3, I am going to on A. Okay, on C, of course, you know that we have to go back to the beginning. So that's C. Likewise, on 4, if I read A, I go to 5. If I read B, that means I have read A, B, A, B, B. Right? A, B, A, B, that's a prefix of P. And then now, instead of reading A, I'm reading B. Okay. Okay, so in this case, there is no prefix, that's also a suffix. So that means from 4 on B, we will need to go back to the beginning. Okay, similarly on C, we also should go to the beginning. Now on 5 on C will go to A, but on A or B, okay, it will all go to 0, go to the beginning again. Oh, sorry. On C, so if I read A now, then that's not doing so quick. If I read A, that means what I have is A, B, A, B, A, A. Right? If I read A, so at least I know this. So this prefix is a suffix. So that means from 5, I am going to here on A. Only when it's a C. So only when it's on B, sorry, not only on C. So when it's on B, so let me erase this and say here's B. Okay, so on this case, A, B, A, B, I'm sorry, no, I forgot an A here. So there's an A. I forgot A here, so let me rewrite it. So A, B, A, B, A, B, A, B. So you can see here, this is a suffix. So that means this is 4, right? So there's a 1 to 4 is a prefix of P, that's also a suffix, which is the largest. So that means from 5 on B, I'm going to go to 4. B. Okay. So when we are here, I have seen A, B, A, B, A, C. Oops. Okay, and so from here, if it's a B, where should I go to? So that means I have read A, B, A, B, A, C, B. So you should go back to the very beginning. And so let's see, I have room, do I have room? I should have room. Let's just go here. B. Okay, likewise on C. And then once I'm here, I have read A, B, A, B, A, C, A. So now I have reached the final, the acceptance state, the accept state. So then, of course, on A, where should I go to start a new matching? So here we have A, B, A, B, A, C, A. So the matching will start. Let's go to 1. Okay, and then on B, that means I have this, so this A, B is the matching, so that go to 2. So that now I have here, B, and then C, of course, it will go back to the beginning. So where is this? And this is C. All right. So that is this DFA. Okay, so this table represents this DFA, and this is looking at the state. So on this prefix of the input string t sub I, so it should be just t1 to I, right? So this is the change of state. Okay, so that is what this DFA indicates. So we have already seen the pseudocode. So that is the construction of automaton, deterministic automaton for matching all appearances of the pattern in a given input. So that is the end of this video. So we are going to look at a new algorithm in the next video, which is a K MP algorithm. So let me stop here for now.